Hi all, my name is Nisha and I'm a PhD student from University of Queensland, and I'm happy to be presenting virtually on my PhD project on this workshop on peatlands. And this is really linked to my PhD project, which is also on wetlands degradation and restoration through reconstructing peat, hydrology, and vegetation dynamics using paleoecology and geochemical proxies. So before I start, I just want to give a brief overview of what I'll be presenting today. I will start with the project background and some background on the study sites, and then I'll go on to making a case on why paleoecology and geochemical proxies are important tools for restoration. I'll also be using some preliminary analysis that I've done for my Sabangau peatland site to bring across these points. So let's start with project background. So the main project objective is to investigate the use of paleoecology and geochemical proxies as a tool to uncover the recent and long-term responses of peat, hydrology, and vegetation systems to both anthropogenic and climate-driven degradation for restoration purposes. And I have two different study sites. One of it is in Central Kalimantan and the other one is in North Stradbroke Island in Australia. So if you just look at these two sites, they haven't been degraded. So you can see that the kind of like vegetations that takes over degraded peatlands are similar, and they are like usually sedges or grasses. And this is something that we see in degraded peatlands or wetlands. So just zooming into individual study sites. So for the North Stradbroke Island, I took peat cores from two different wetlands that are close to the coast, and then for the Sabangau peatlands, they're usually inland, and the peat cores were actually provided by Professor Angela from Exeter University. Okay, so for both sites, they have gone through some form of degradation. So for the Sabangau peatlands, a lot of land has been destroyed or deforested because of logging, commercialized logging, as well as plantations such as oil palm plantation. And of course, when this happens, they usually construct canals either for irrigation purposes or also to transport logs out of the catchment. And then for the North Stradbroke Island, the main degradation is actually sand mining that result in a lot of deforestation, and it also always affects the wetlands, which are usually in the neighboring sites. And for urbanization and human settlements, such as construction of roads, and houses, they are similar for both sides. And then extreme climate events such as El Ninos are also similar for both sides. So of course, when you see the both governments in the both countries, has been coming out with a lot of restoration plans and also regulations and managements for fires and also for the other impacts of this degradation. But the two common themes that I see is actually rewetting. So for North Stradbroke Island, I see that they actually construct culverts to actually, join in or to ensure the rerouting of drainage to where your swamps are or your marshes are or your creeks are. And then for for Sabangau peatlands, usually block, the canals using dams so that, water can overflow out to the catchment, especially to increase the groundwater level of the peatlands. And then for revegetation, it's also the same for both sides. We see a lot of replanting of tolerant species, either native species we see in Sabangau peatlands, and then pine species that we see that was revegetated in those sand mining areas, but they are not native, but they are able to tolerate a lot of harsh conditions. But the main objective is still the same. You want to try to raise humidity, lower temperatures, and also reduce fires, stabilize the hydrology and degraded peat and soil to prevent erosion, and also to have this constant input of organic matter so that you can build up your peat accumulation again. So why is then restoration improvement needed, right? So the main reason is because there are limited success in the current methods. As we can see, there is still increasing fire risk, and also there is an increasing, failure of survival of the vegetation species. So the main important thing is to try to improve the understanding of the degradation first. So because a lot of these degradation studies are based on short-term studies, so they did not really include, or there is a lack of understanding of the resilience and feedbacks between the peat hydrology and vegetation system. So if I can bring your attention to the Forking et al. 2010, you can see that the systems are connected. So any impacts to the runoff or the groundwater table level will affect the peat decomposition, for example, and these conditions will affect the kind of vegetation that are able to thrive. The vegetation in turn provides, the different organic matter to the peat. So, different organic matters will have, different hydraulic conductivity, and then hydraulic conductivity affects how your peat can store water. So that in turn affect your groundwater table level as well. So there are a lot of connections, and the most important thing is that they happen in different time scales. So it's really important to have this long-term understanding to find out about the different time scales. And another reason is, of course, standard prescriptions of the restoration efforts. As we can see, we usually use like tolerant species for revegetation, and there is really no way to see if this is successful or not, because most of the monitoring are short-term, or there is no pre-degradation baseline that we can compare these restoration efforts or evaluate these restoration efforts. So this is where the project comes in, which is trying to use paleoecology and geochemical proxies as tools for restoration. So if you look at the indicators, so the main benefits of these proxies is that they provide indicators of degradation impacts. So as I was reviewing a lot of different studies across tropical and subtropical peatlands that use proxies, there are these proxies that were used to reconstruct like hydroclimate or environmental conditions, but a lot of it is not being used for degradation, which they can be actually used for degradation. So I'm just gonna, pinpoint certain of them. So things like pollen and spores, they are actually really good indicators of vegetation dynamics and environmental changes. And if you group these different species that you identify to the different ecological vegetation groups, it can also provide understanding about the moisture, the peat conditions. So for the Sabangau peatland initial data, what I did was I actually grouped them into different vegetation or forests. So we have things like coastal vegetation, open vegetation that you usually see when there's a lot of degradation. We also have lowland mixed swarm that can tolerate fluctuating conditions and so forth. Okay, and then let's go back to tested amoeba, which is another proxy, which majority of the papers that I reviewed talks about it being a very good indicator of hydrological conditions. So majority of the papers actually use these transfer function models to between modern tested amoeba species and groundwater level or pH of peat to try to reconstruct the past groundwater level trends using this fossilized tested amoeba that they see in their peat cores. So for the Sabangau side, I actually see a lot of these H. subflora species, which is a good indicator of dry conditions when they are very small in sizes. So I've been using it to reconstruct groundwater level. And then lastly, we also look at micro and macro charcoal concentrations, which is good, to tell us about the fire events, whether they are localized or they are regional fire events, for example. So these are the different, paleoecology proxies that I use. I won't be elaborating now. I will elaborate it in the next few slides. So using these paleoecological proxies, right, the geochemical proxies can be used as verification to these proxies. So things like carbon nitrogen concentration are good indicators of peat accumulation and decomposition. And of course, a lot of people use it to generate the carbon storage and carbon density. And then for the peat humidification analysis, it's also a good verification of the indicators of peat decomposition. And for the magnetic susceptibility and elemental concentration proxies, it's good to try to understand about degradation history, such as erosion, whether there is any chemical reactions with degradation, pollutants, for example. And then there are also certain elemental that in peat, in organic rich peat, that are very resistant, such as titanium. So if there's any changes in that, we can tell about the preservation quality of the peat as well. And lastly, radiocarbon and radionuclides dating, such as carbon-14, lead-210, and cesium-137 are very useful in trying to understand when this degradation happens. And of course, I do acknowledge that these individual proxies have their own limitations, when you look at it by itself. But if you look at it together, you can use its different multi-proxies as a verification of the different indicators of both, of the responses of peat, hydrology, and vegetation dynamics towards degradation. So these are the different proxies that I use for the Sabangau peatland peat core, but I'm not going to go in depth about the different trends for each because I'm still in my preliminary stages of analyzing the data. But I just want to bring attention to the clustering analysis that I did for using the pollen data. It was interesting that they actually captured immediately 4 different clusters, and 2 of the clusters are actually just going back to the last 400 years. We see a drastic change in terms of the vegetation dynamics, which really reflects the impacts of the recent anthropogenic degradation. So also using these long-term data, we are able to provide pre-degradation baseline and time frames of recovery. So what do I mean by this is that I'm just going to explain it using the same data set for my Sabang peatlands. So if I just bring your attention to this plot, this black line here refers to the groundwater level index for my tested amoeba counts, and then the bars here, the histograms here refers to the fire severity for my charcoal concentration, and then I have I actually also identified the dominant vegetation species that I find in the different time periods for my pollen data set. So if you look at this red color part, this is actually our 1900s to 2000s, and then this is between 1700s to 1900s. So you can see that it's very, there's lower fire severity in the past, and then you can also see that the dominant species was actually freshwater swarm because it was wet and there was not much fire severity. But then once it dips to a certain level, we suddenly see freshwater species, going really down, and then it was actually replaced by lowland mixed swarm species because they are able to, survive in a lot of fluctuating conditions. And again, when they reach a certain groundwater level, we start seeing our freshwater swarm being the dominant species again. And it's interesting that, there is a period where you don't really see any more freshwater species is when there was a lot of fire events, fire severity, and also groundwater levels was consistently low. And the species that comes back wasn't lowland peat swarm, but actually early succession peat swarm species, which are usually vegetation that comes in when there is very large-scale degradation. And then it's also interesting that, once groundwater level actually picked up, in the recent years, actually I started to see the similar freshwater swarm species that I see in the past. So this really tells me about a tolerant vegetation species that survive different degradation, whether is it, fire events or whether is it low drought conditions, for example. And also tells me about the minimum groundwater level that is needed for the replantation of these species, for example. So these are important information that we can use for our restoration. And in addition to that, they also tell me about the time frame of the recovery of the different species. What are the lags for freshwater to come back again after fluctuating groundwater level conditions, and what are the thresholds that we see here that we can use as well. So these are really important information. This is really preliminary studies, so I only went back up to 1700 here. But if you look at before 1700, the kind of data sets, the resilience, the lags are very different from what we see today. So I will elaborate more on this on my paper in the future. Okay, so the second point that I want to really bring out is that using this long-term data, we are able to estimate the total losses of degradation. And I think this is really important if you want to make a case of why restoration is needed, because majority of the data that has been done is usually like the immediate carbon loss, for example, the fire events, but usually these carbon loss are very long-term because it includes lags from emissions of oxidative decomposition, of exposed deep organic rich peat layers, emissions from vegetation changes, and also fluvial carbon that got leached out into your waterways because the peat is decomposing. So either as DOC or POC. So a lot of this information we can actually get from the total below ground and above ground carbon losses that we can calculate from the peat cores by looking at the carbon concentration proxies or even the vegetation proxies from the pollen. It can really tell us about what kind of actual carbon loss that they are getting. And if you're interested more on the fluvial carbon, we can use proxies such as manganese concentration in peat to give us an idea about the fluvial leaching conditions, for example. So this information is really important, I feel, to make a case of why restoration is needed, but also give us an idea of how severe are these degradation that has been happening in the recent times, especially. And lastly, a lot of this long-term data can be input into peat hydrology models. There are many hydrology models such as HPM, Holocene peat model, DigiBog, that have been used recently to try to project peat accumulation as well as groundwater level for future scenarios, whether it's degradation or restoration efforts. I will briefly talk about the model. So basically, they are the same. They do think about the feedback between the different systems. They use a lot of different parameters to think about the different feedbacks, but majority of these data set, they actually are very recent. They use instrumental data set mainly, so they couldn't really capture a lot of the different time scales of the different interactions and responses between the systems. So we do, what we can do is actually use this long-term data to try to replace some of the variables of things like vegetation. We can use the pollen data, for example, and in the water table, we can use the groundwater level that we reconstructed from tested amoeba and so forth. And in addition to replacing the web parameters with long-term data, I think it's also very important to actually incorporate long-term information on the resilience, the thresholds, and the lags that we have already found out, that we talked about previously, and input this into the model so that we can help to generate a better projections of future degradation and restoration as well. Okay, so just concluding remarks, there are a lot of potential of these boxes when they come together to provide insights on the peatland responses to anthropogenic and climate-driven degradation. So things that we know that we can use these boxes for, like vegetation dynamics, groundwater level, peat decomposition, and accumulation risk, and also degradation history, such as our fire events. So I think it's really important when all these data set comes together, we can actually provide information on thresholds, information on lags that is really needed for revegetation and reverting strategies, and also the time frames of what the recovery that is to be expected. And then, of course, inputting all this long-term data into projections models would be really useful for us to really determine what kind of restoration we want to take place in the future as well. And with that, I end my presentation, and I hope I make sense. And if you have any question about my data set, like I said, they are mostly preliminary, and I'm still currently analyzing them, but you can email me through this email. Thank you.